The exploration of the outer solar system has undergone a profound transformation in recent decades, revealing that the potential for life is not confined to the traditional habitable zones around stars. Enceladus, the sixth largest moon of Saturn, has emerged as a central figure in this scientific revolution. Despite its small size of only 500 kilometers in diameter, this icy world defies thermodynamic expectations by maintaining a global liquid ocean and vigorous hydrothermal activity beneath a frozen crust. The discovery of this, ice on the outside, fire on the inside, duality has shifted the focus of astrobiology toward ocean worlds, where internal heat sources rather than sunlight drive the chemical engines of potential biology. To truly grasp the significance of Enceladus, one must adopt the cosmic perspective championed by Carl Sagan, who famously described Earth as a pale blue dot. He reminded us that our world is but a small stage in a vast cosmic arena, and discoveries on moons like Enceladus challenge our perception of biological centrality. To understand the hydrothermal activity and the potential for life on this moon, we must essentially invent the universe, as Sagan suggested in his apple pie analogy, recognizing that the calcium, iron, and carbon detected in Enceladus plumes were forged in the hearts of stars that exploded billions of years before our solar system existed. Imagine an absolute desert of ice where temperatures are so extreme that oxygen would turn solid, and where the silence of eternity is the only constant. Yet, beneath this impenetrable armor of frozen crystal lies a beating heart of fire and fury, a restless ocean that defies the laws of planetary thermodynamics by launching colossal plumes of vapor and organic matter thousands of kilometers into the vacuum of space. Enceladus is not merely a frozen satellite, it is the most vibrant chemical laboratory in the solar system, a world that should be dead but chose to burn. As physicist Brian Cox describes, life is a temporary structure on the long road from order to disorder, or entropy. Enceladus represents a fascinating anomaly where Saturn's tidal energy slows this inevitable march toward a total freeze, maintaining a dynamic system of order in the cold reaches of the outer solar system. The primary goal of this investigation is to explore the geophysical and geochemical mechanisms that allow a frigid external crust to coexist with an active internal hydrothermal system, evaluating what this means for the possibility of life elsewhere in the cosmos. Our current understanding of Enceladus is the result of a scientific journey that transformed a faint point of light into a high-priority target for space exploration. This journey began on August 28, 1789, when the British astronomer William Herschel discovered the moon using his massive 40-foot reflecting telescope, which was the largest in the world at the time. This discovery was a feat of precision, made possible during Saturn's equinox when the rings were seen edge-on, minimizing their glare and allowing the faint moon to be spotted for the first time. For nearly 2 centuries, Enceladus remained little more than a mysterious dot, notable only for its exceptional brightness, which suggested a surface composed of pure, highly reflective ice. It was not until the Voyager 1 and Voyager 2 missions passed through the Saturnian system in the early 1980s that we saw the first evidence of geological complexity, with images showing vast, crater-free plains that hinted at recent resurfacing. The real paradigm shift occurred with the Cassini-Huygens mission, which entered orbit around Saturn in 2004. In 2005, Cassini detected massive plumes of water vapor and ice crystals erupting from the moon's south pole, confirming that Enceladus was geologically alive. Throughout its 13-year mission, Cassini acted as an in situ laboratory, performing 23 close flybys and even diving through the plumes to taste the materially jaded from the interior. These encounters allowed instruments like the Cosmic Dust Analyzer and the Ion and Neutral Mass Spectrometer to identify a salty ocean in contact with a rocky core. More recently, in 2023, the James Webb Space Telescope used its incredible sensitivity to map a water vapor plume extending over 10,000 kilometers, more than 20 times the diameter of the moon itself. Furthermore, a 2025 analysis by researchers at Oxford University has confirmed significant heat flow at the moon's north pole, suggesting that Enceladus possesses long-term thermal stability that is crucial for the development of life. Geological activity on Enceladus is almost entirely concentrated in the south polar terrain, a region defined by 4 massive, parallel fractures known as the Tiger Stripes. These fissures, named Alexandria, Cairo, Baghdad, and Damascus, are approximately 130 kilometers long and 35 kilometers apart, flanked by ice ridges that indicate a history of tectonic expansion. Infrared analysis has shown that these stripes are significantly warmer than their surroundings, acting as the primary escape valves for the moon's internal energy. The mechanism behind the plumes is a form of cryovolcanism where pressurized ocean water finds its way through these cracks into the vacuum of space. Upon ejection, the water flash freezes into vapor and ice grains, much of which falls back to the surface as fresh snow, explaining why the region is almost entirely devoid of impact craters and has a surface age of less than 1 million years. The physics of these fractures are unique in the solar system and were explained by a zipper model in recent research. The first fracture, likely Baghdad sulcus, formed as the moon cooled, causing the subsurface ocean to freeze and expand, which increased internal pressure until the thinnest part of the crust, at the poles, split open. Once the first crack formed, the weight of the falling snow and ice on the edges caused the ice sheet to flex and bend, triggering a second parallel crack exactly 35 kilometers away. This process repeated to form the 4 stripes we see today. This specific spacing and the ability of the cracks to remain open are only possible because of Enceladus' low gravity. On a larger moon, the weight would have forced the fractures to close. Tidal forces from Saturn continue to stretch and squeeze these cracks, preventing them from healing and ensuring a constant flow of material from the ocean to the surface. The definitive proof that Enceladus hides a global ocean, rather than just a regional sea, came from a detailed study of its libration, which is a subtle wobble in the moon's rotation as it orbits Saturn. If Enceladus were solid all the way through, its rotation would be very rigid. However, precise measurements from the Cassini mission showed that the wobble was far too large for a solid body. The only physical explanation that fits the data is that the ice crust is entirely detached from the rocky interior by a layer of liquid. This allows the crust to slide over the ocean, responding more dramatically to Saturn's gravity. This global ocean is believed to be salty and alkaline, sitting directly atop a porous rocky core, creating a massive environment for chemical exchange and potential biological activity. The internal structure of Enceladus consists of several distinct layers that work together to maintain this habitable environment. At the surface is a global ice crust with an average thickness of 20 to 25 kilometers, which acts as a powerful thermal insulator. However, this crust thins to just 1 to 5 kilometers at the South Pole, providing a window for the plumes to escape. Beneath the ice lies the global salty ocean, which serves as a medium for the chemical reactions necessary for life. At the center is a rocky core with a radius of about 200 kilometers. Crucially, this core is not a solid block of stone, but is instead highly porous and permeable, which allows ocean water to flow deep into its interior, where it can be heated by the friction caused by Saturn's gravitational tides. Explaining how such a small moon can stay warm for billions of years was one of the greatest challenges in planetary physics. Radioactive decay alone would not provide enough energy to prevent the ocean from freezing in just 30 million years. The solution lies in a process called tidal heating, but it occurs in a very specific way within Enceladus' porous core. Because the core is composed of fragmented rock that is not consolidated, the gravitational pull of Saturn causes these fragments to rub against each other as the moon moves through its elliptical orbit. This friction generates a tremendous amount of heat, up to 30 gigawatts of power, which is nearly 100 times the energy produced by radioactive decay alone. This porous core acts like a massive hydrothermal pump that operates in a 4-stage cycle. First, cold, dense ocean water infiltrates the deep pores and cracks of the rocky core. Second, as this water travels through the core, it is heated by the friction of the shifting rocks to temperatures exceeding 90 degrees Celsius. Third, the heated water becomes less dense and rises in vigorous convection currents back toward the seafloor. Finally, this hot water is focused in specific areas, particularly under the South Pole, where it thins the ice crust and feeds the geysers. This stable thermal balance is what allows the ocean to persist over geological timescales, providing the necessary time for life to potentially emerge and evolve. Proof that the interior of Enceladus is truly hot, rather than just warm, came from the discovery of tiny nanoparticles of pure silicon dioxide, or silica. These particles were detected by Cassini's instruments both in the plumes and in Saturn's E-ring. On Earth, the formation of pure silica grains of this specific size, between 2 and 8 nanometers, occurs almost exclusively in hydrothermal environments where water interacts with rock at temperatures above 90 degrees Celsius. This serves as a geochemical thermometer, confirming that deep-sea vents on Enceladus are actively pouring hot, mineral-rich water into the ocean. The journey of these silica particles is a testament to the moon's internal dynamics. They form on the seafloor during intense water-rock interactions and are then carried by upward currents from the bottom of the ocean to the base of the ice crust. The fact that they reach the surface and are ejected into space without being dissolved indicates that the hydrothermal transport is extremely fast and powerful. This provides clear evidence that Enceladus has the 3 essential ingredients for life: liquid water, chemical complexity, and a consistent source of heat and energy. In October 2015, Cassini performed its deepest dive into the plumes, flying just 49 kilometers above the surface to sniff the gas for molecular hydrogen. The detection of significant levels of hydrogen was a milestone for astrobiology because hydrogen is a direct product of serpentinization. This is a chemical reaction that occurs when water reacts with iron-rich minerals like olivine at high temperatures. In the dark oceans of Earth, this process creates the chemical energy that sustains entire ecosystems in the absence of sunlight. On Enceladus, molecular hydrogen represents a continuous source of chemical food that is being produced right now. This chemical energy is particularly important because it can drive a process called methanogenesis. Microbes known as methanogens can combine molecular hydrogen with carbon dioxide, which was also detected in the plumes, to produce methane and metabolic energy. The presence of both hydrogen and methane in the plumes suggests that Enceladus has a functional biological or geochemical system that perfectly mimics the precursors of life found on our own planet. This makes the moon one of the most promising places in the solar system to look for active extraterrestrial metabolism. The plumes of Enceladus carry much more than just water and salt. They are loaded with a sophisticated array of organic compounds. While Cassini initially found simple molecules like methane and ammonia, later analyses of data from high-speed impacts revealed the presence of complex organic macromolecules containing hundreds of carbon atoms. These molecules have aromatic and aliphatic structures, along with nitrogen and oxygen, which are the fundamental building blocks of biology. The discovery of these heavy organic molecules proves that sophisticated chemistry is occurring within the subsurface ocean. A variety of organic compounds have been identified through these samples. Simple organics like methane and ethane indicate basic metabolic possibilities, while more complex macromolecules like esters, alkenes, and ethers serve as the precursors for lipids, which are essential for building cell membranes. Nitrogen-bearing compounds like cyanate and ammonium are preprocessors for amino acids. Because these molecules were found in fresh ice grains rich in salts, we know they come directly from the liquid ocean and are not simply the result of radiation hitting the surface ice. This free sampling provided by the geysers allows scientists to study the deep chemistry of an alien ocean without ever having to land or drill. To understand the habitability of Enceladus, scientists look to the Lost City hydrothermal field in the Atlantic Ocean as a terrestrial analog. Unlike typical volcanic vents that are acidic and extremely hot, the Lost City is an alkaline system driven by serpentinization. It emits fluids with a high pH, rich in hydrogen and methane, creating a thriving environment for life far from any sunlight. Chemical models of Enceladus Ocean suggest a striking similarity, with a pH estimated between 10 and 12. This makes the ocean a soda ocean, similar to alkaline lakes on Earth like Mono Lake in California, where specialized life forms flourish. The habitability of this alkaline environment is supported by 3 pillars. First, there are strong energy gradients. The difference in pH and temperature between the hydrothermal fluids and the surrounding ocean creates the electrochemical potential that primitive life can exploit. Second, there is an abundance of nutrients. Cassini has detected the essential elements for life, known as CHNOPs: carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. Finally, The porous core model suggests these conditions have been stable for billions of years. While a high pH might seem harsh, many extremophiles on Earth thrive in such conditions, making Enceladus a prime candidate for a stable, habitable world. One of the most persistent mysteries was the Mimas paradox. Mimas is another moon of Saturn that is closer to the planet and has a more eccentric orbit than Enceladus, which should mean it experiences much stronger tidal heating. Yet, Mimas appears to be a geologically dead and heavily cratered world, famously resembling the Death Star, while Enceladus is highly active. The resolution to this paradox lies in the initial thermal state and internal composition of the two moons. Enceladus has a significantly higher density than Mimas, indicating it contains much more rock and, therefore, more radioactive material. This extra heat kept Enceladus ice warm and flexible in its early history, allowing it to dissipate tidal energy much more efficiently in a positive feedback loop. Mimas, being colder and more rigid, behaves like a solid insulator that cannot trap or generate heat through tidal friction. Thus, Enceladus entered an excited, high-energy state while Mimas remained in a basic, frozen state. This comparison highlights that a moon's internal structure and history are just as important as its orbit in determining its potential for habitability. Leading-edge research from 2024 and 2025 suggests that Enceladus activity might not be constant, but instead operates in limit cycles, lasting about 10 million years. In this model, the moon goes through 3 stages. Currently, Enceladus is in a freezing stage where the ice shell is thickening, which pressurizes the ocean and forces the geysers to erupt. Eventually, the orbital eccentricity increases enough that tidal heating takes over, leading to a melting stage where the shell thins dramatically. Finally, a resonant libration stage occurs where the moon generates massive amounts of heat. The high luminosity we see today is likely a relic from the last melting episode, meaning we are observing Enceladus at a very special time in its cycle. The future of exploration will target this activity directly. NASA's proposed Enceladus Orbilander mission, a flagship concept costing over $2.5 billion, is designed to launch in 2038 and reach the moon in the 2050s. This spacecraft would spend a year and a half in orbit sampling the plumes before landing near the Tiger Stripes for a 2-year mission. It will carry a life detection suite equipped with instruments to search for amino acid distributions, lipids, and even genetic biopolymers using a nanopore sequencer. By analyzing the free samples delivered to space, the mission aims to provide a definitive answer to whether life exists in the depths of Saturn's most mysterious moon. In conclusion, Enceladus forces us to confront the great question of whether life is a cosmic imperative that emerges wherever there is water and energy, or if we are a statistical anomaly in a sterile universe. The discovery of a stable, salty ocean with active hydrothermal vents and complex organics has made Enceladus the most accessible and promising laboratory for astrobiology in the solar system. As Neil deGrasse Tyson often reminds us, we are made of stardust, connected to the same atoms found in the plumes of Enceladus. Understanding this moon is, in a sense, understanding our own chemical history. The exploration of these distant moons is the fulfillment of our destiny as travelers and explorers. If something beneath the ice of Saturn is indeed looking back at us, the discovery would reshape not only science but our entire understanding of humanity's role in the cosmos. Enceladus, with its external ice and internal fire, remains a silent invitation, sending its plumes of mystery into the void and waiting for us to develop the technology and maturity to finally decipher the secrets hidden in its alkaline abyss. Whether or not we find life, the search itself represents the awakening of our cosmic consciousness.